Thank you, Professor Lakina, and thanks to JNU to organize such a nice meeting, especially Ram. So, my talk is on MHD turbulence, and of course, this is this is a remembrance of Suranam Chandrasekhar. So, I will touch upon his work. I'm not really astrophysicist, so I don't know a lot of things about Chandra, but there was pretty nice talks by various people, including Vinod Krishan, Professor Bhuti. I'll just touch upon some of his work in this field. Okay. So first, these two books I didn't see it mentioned, so I would like to recommend to especially students. These are biographies of Chandra. So these by Professor Wally, who is very well known, and Miller. So this is in fact it came recently, and it has more details about what all happened in Cambridge. I think this is a first part is very engaging. So I really recommend this book for anyone who's interested in Chandra's life. So, like it was mentioned, no, I mean, his work on white dwarf was very early, and in fact, he told everyone in Cambridge. Nobody found a flaw, and they kind of agreed, but nobody supported really. This was told by Professor Bhuti very clearly. So I think we should learn a lesson that we should continue or whatever we believe in, and of course we should be strongly supporting it with mathematics and arguments, but no need for really looking up to an expert saying okay, great or good. You should continue to do it if you believe it. Okay, anyway, so let's first, before MHD, we need to get into hydrodynamics. And Chandrasekhar, I mean, this is around 50 to 60. Okay, I mean, there's a nice article by Srinivasan, KRS, in Annual Reviews of Fluid Mechanics. Okay, this came in, I think, 21 only this year. So this covers is article on Annual Reviews of Fluid Mechanics on Chandrasekhar's on hydrodynamic turbulence. Okay, so this is a very nice article. It's a pretty short one, and gave a set of lectures, and that lectures have appeared in a book. In fact, it is not authored by him. His student Spiegel, who compiled those notes, and this is nice one. There are flaws. I mean, definitely things are advanced in the theory of turbulence. So and there are some problems in some of the work in this book. But so I wrote another book. We wrote a book on turbulence. So here I describe some of Chandra's derivation on dissipation range of spectrum. Some of you may not understand it, but don't worry. So some of it is covered in this book. But it's a nice book. It's a pretty thin book, around 100 pages. Of course, Chandra's style is very mathematical and to the point. Okay, I mean, just like extremely thorough mathematical derivations. So let's go to hydrodynamic turbulence. So for that, I see that there are varying audience. So I just want to go slow. So I apologize for people who are experts, but for students especially, I just want to go slow. So this is the Navier-Stokes equation. Okay, this equation for just fluid flows. There's no magnetic field in this. Magnetic field will come in a while. Just wait for a few minutes. So this viscous term and pressure term. Okay, and so Kolmogorov gave a theory for this. Okay, so there are of course more work, but most important name is Kolmogorov in 1941, and he considered incompressible flows. And Chandra also basically focused on, for this set of work, on incompressible flows. Well, for MHD there is in that book it is incompressible, but MHD there are compressible components, like what Avinash Khare was telling today morning. So let's look at another approximation called homogeneous and isotropic. Homogeneous and isotropic means flow anywhere in that box is approximately similar. So you can just go to some distance, it will be the same. And isotropic, if you go around in very angle, and then you'll find that properties don't change. And one such, I can see one such instance of that turbulent flow is here. This is vorticity squared. So This is what we plotted is what is Z squared, and is somewhat random. I mean, of course, there are gaps in here. So this homogeneous and isotropic. Okay, is one example. And if you're away from the walls, in like say for example in a galaxy, you don't go to the center of the galaxy. You just take any box somewhere in between. That will be homogeneous and isotropic approximately. Now, for this Kolmogorov theory, it is way back in 1941. Take 2 points, Ux, and so I am coming to it because Chandrasekhar wanted to generalize it for MHD. That's what my motivation is, why I am getting into hydro. And this theory is very nice. So, along with Chandrasekhar, we can also remember Kolmogorov. So, there are 2 points which are separated by distance r, vector r actually, vector r here. So, Ux and Ux, this is x and this is x plus r. And the velocity field at these 2 points are Ux and Ux plus r. And so what Kolmogorov showed, that if you take the difference between the velocities, it's a vector of course, velocity, so difference, but take the component along the separation, so parallel component. So take the parallel component of u along here, take a parallel component of u along here, and cube it. So cube it, then we get this equals to minus 4/5 this is a pi, which is cascade rate r. Cascade rate is if I shake up a fluid, take a bucket of water and stir it, then energy cascades from large scale to small scales. Okay, so it finally gets into heat. So that is called cascade rate. So this is pi. Okay, and this is of course in the turbulent limit, Re going to infinity limit. Okay. Now. So another derivation is connected to this, but let's ignore it. So this is a Kolmogorov thing. And how do we derive it? Because we look at Chandrasekhar's paper, you'll find that he is following similar lines. So it's slightly daunting. I mean, algebra is a bit tedious, but you take these 2 points. So prime is x plus r, and u is without prime is r x. Okay, so the distance, so that is a 2-point correlation. Okay, so velocity field at 2 points, and take a partial derivative d by dt, and there is a derivation, no need to worry too much about it. But finally you see that there is this term which is very similar to in fact this is what has Kolmogorov in it. Okay, in his final result. Now it's a divergence. So divergence with L. I made slightly with R, you should say, with R. Okay, so there's a difference in notation. So with R. So this point, so divergence with R vector, okay, of these two, this quantity, this structure function is called. Okay. Now this is the force which is forcing here, and this viscous term. So Kolmogorov made an assumption that viscosity goes to 0. So this term is dropped out, and you essentially equate these two terms. This term, which is nonlinear transfer, and forcing term. Pressure incidentally drops out because of incompressible condition. Pressure is gone. Okay, so this pressure term is gone, and so this derivation, well, of course, is property of Navier-Stokes equation, that it turns out it simplifies a lot for incompressible limit, and the divergence of r dot that structure function, okay, right now is a vector, so delta u squared delta u equal to, so energy supply rate for this assumption, this is a vector, this is a vectors. So energy supply rate, if I force at large scale, then this is epsilon, sorry, this is minus epsilon. Okay, so there's a plus sign, and we take the divergence. Basically, what is the divergence in 3D? Is 1 is r squared d by dr r squared s3. Okay, and this is epsilon, and you can integrate this. This is 1D equation. Okay, so this is 1D. So s3 we can just integrate it. It comes out to be minus 4/3 epsilon r. This S3 is slightly different than Kolmogorov's S3. That was had in the next line. So this is a simple derivation, which simplified version of the derivation. But this all, everything is there. Okay, I mean, I just giving you a sketch. Now this is in 41, and of course there are a lot of people who wanted to generalize it to more systems like thermal convection, MHD, and so on. So that's what Chandrasekhar wanted to do it for MHD. So MHD, of course, it was Avinash had some of it in his slide, but not fully. But let's see. So MHD has two equations, one for the velocity field and one for the magnetic field. So just imagine that there are magnetic field fluctuations, and there could also be a mean magnetic field. Huh? So there is right now I have not put mean magnetic field here. So we can have a mean magnetic field B naught. So total magnetic field is B equal to B naught plus B. Okay. So we have this this stuff. So we write down the equation, and this term is the J cross B force, Lorentz force, and the equation for magnetic field, this follows from another Maxwell's equation. Okay. Now, so we have two diffusive parameters. One is kinematic viscosity as usual, another one is magnetic diffusivity. Okay. So these are two diffusive terms, and the four nonlinear terms. So this is one nonlinear term, one nonlinear term here, one nonlinear term here, one nonlinear term here. This under some simplification, it comes as that B dot red B. Okay. So we have four terms. So it is not now. I want to generalize Kolmogorov theory for MHD. That was a motivation of a lot of people, and is not all that straightforward. Okay. So here there is a well, let me ignore this. So there are two Reynolds number. One is UL by nu, another one is UL by eta. Is my whole screen visible? I mean, our bottom is cut, is it? Ram, is it my whole screen is visible? No?
Yeah. We can see your whole screen.
Okay, great, thanks. Okay. So this UL by nu and UL by, so there's magnetic length, but don't worry about it. Right now, for today's talk, we don't need to worry about that part. So one important thing here is that this alpha wave. Okay. So we have mean magnetic field B naught. Okay, I took from a website. In fact, I should have cited where from. So magnetic field lines are basically like strings. Okay, a thread, a rubber band actually, not thread, rubber band. And when you pluck a rubber band, then you get waves. Okay, so these are the waves. So these are fluctuation in magnetic field. This is magnetic, and velocity field either in the same direction or opposite direction. Okay, so that's so these are the alpha waves. Okay, now this can be easily derived by linear limit of MHD. Nonlinear term, we drop it, then we get nice alpha waves. Okay. Now this will come later, so we want to make sure that we have this stuff. There are two types of alpha waves. If this is a B naught, then one alpha wave goes in that direction and one goes in that direction, and this is called Z minus and this is Z plus. No, sorry, this is Z plus along B naught and this is Z minus. Okay, so these are called Elsasser variables, and they are defined as this, and Z minus is U minus B. Okay. So these are change of variables, but they are basically waves which are going in the direction of the magnetic field or opposite direction. Okay, and okay, so these are alpha waves. Now Chandrasekhar, this is 1951, so I'll just show you the paper submitted in 50, and it appeared here in this 51. Okay, so there is a noise. Okay, so invariant theory of isotropic turbulence in magnetohydrodynamics. Okay, now he is trying to basically work out like what he's trying to work out this equations in similar to Kolmogorov theory. So I will not go through the all the. I mean, this is a usual Chandrasekhar style. He is very mathematical, detailed, and so you can see that there are triple correlation terms. So this is like so if your equation for u dot, then right hand side is del j uj ui. But if I write down equation for double correlation u prime, then this will be 3 of u's, right? Del j uj ui. So these are triple correlations. That's why you see u here. Okay. So we want to write equation for, let's say, kinetic energy correlation u prime. then you'll have this term which is the Kolmogorov term, but the other term is in ui del j bj bi. So this is a magnetic term, uj bj del j bj bi. Okay, now this term is a complex, it's a magnetic coupling of magnetic field with velocity field. That of course Kolmogorov does not have it. Okay, now these are the cross term which Chandrasekhar was trying to close. Okay, now Kolmogorov theory, as I said, is very fortunate that he has only one structure function, and that is equated to the forcing rate or dissipation rate. But here, of course, with these terms, it becomes a problem. In fact, this paper, he could not get a relation like Kolmogorov relation. In fact, that remained a problem for many years in future. Okay, of course, we understand much better than what Chandrasekhar was trying to do in 51. But this is a paper about. I mean, he was trying to really get these correlations closed, and this, if you are aware of turbulence, this is called closure problem. In fact, also there in kinetic theory. So second order correlation will depend on third order correlations, third order will depend on fourth on fifth, and so on. So we need something good to close it. Okay, so I'm going to describe a bit later or how to close it. Now, so some attempts like Kreknen, so this is a very famous name in turbulence. There's a paper in 1959, so 8 years after that, and he tried to solve the problem. In fact, he was trying to apply field theory in turbulence. Okay, so field theory is one of the first works of applying field theory, usual field theory, for hydrodynamic turbulence. Kreknen did not really attempt MHD field theory. Of course, he has a very famous theory which I'm going to discuss in a few minutes. But field theory he tried to do, and I will describe that field theory a bit later. Okay, so just to state what he was trying to do, field theory treatment turbulence, and he wrote equation of the Green's function. Okay, now some of you may not understand it, but don't worry, and energy flux. Okay, so I will just sketch it in a while. Okay, so just try to sketch it. Basically he gets relation for relaxation time and Kolmogorov constant. Okay, so that is DIA, which I will not detail it, but I am just telling you what he did. Now there is one more work. This is much later, 1982, by Fournier of Sulheim and Frisch. No, sorry, not Frisch. Pouquet. Frisch is not there. Pouquet, and they are trying to do the field theory in MHD. Okay, this one is similar to what Kreknen is trying to do. Well, and broadly similar, but there are of course there differences, and they try to do this. In the meanwhile, there is a paper by Orzog and Yacoud, but this for hydrodynamics. Okay, so people were trying to apply field theory, which you do in similar thing in particle physics or condensed matter physics. The formalism is very, very similar. Okay. So this is 1986. Now, so his attempt to obtain a closure, but again unsuccessful. Okay, so I will tell you what I did. In fact, I was into this problem. I wanted to release work on this problem, and so I wrote 5 papers on this. Okay, so this is in 2001. No, this is 99. 2001. Well, and you don't need to worry about the titles and so on. So this is a physics report which is very detailed, 150 page long, and there I describe the closure and I solve the problem. I could say that I solve the field theory to first order. That's what I would say. So this also, well, I want to advertise my book. So this is a book on. It has 8 chapters on MHD. So MHD is discussed in significant detail, and these on convection. Okay, it's not quite MHD, but Chandrasekhar also worked on convection. So this very famous book. I hope I'll have time to tell few words about the book on hydrodynamic and hydromagnetic instability, and it's considered Bible. And I'll tell you the story of it when I come to that. So it has some of the Chandrasekhar's derivations. So before we get into field theory, which I will try to sketch it, what I did and what is done in field theory. But before that, I need to tell you that there are two competing theories for MHD. Kolmogorov theory, some people may know that energy spectrum is epsilon 2/3 k minus 5/3 times Kolmogorov constant. Okay, so this is called Kolmogorov spectrum for hydrodynamic turbulence. But what is the theory for MHD? So MHD, remember I had said there are two waves, alphane waves, Z plus and Z minus, and these two alphane waves have their own cascades. Okay, now they have too short a time to describe those stuff, and some of you may not be interested in it, but just to tell you, there are there are two variables, Z plus and Z minus, and they have their own cascade rates, and the equation for them is so we have two variables, so there are two spectrums, Z plus and Z minus, and there are two cascade rates. So one of them have 4/3 power and another one is minus 2/3 power, and he made k minus 5/3. Okay, so overall if you see the cascade rate exponent is 4/3 minus 2/3 is 2/3, but is asymmetric at that present, and this is first derived by Marsh. So I forgot to tell you that this is work by Marsh. He wrote the first derivation, the first formula for this. It's it's not derivation per se, it's a dimensional analysis. That's what is done, and so this one formula for MHD. Other formula, which is very different assumptions, it assumes that the time scale for turbulences depends on the mean magnetic field, this B naught, and 1 by k B naught. It comes from dimensional analysis, and the spectrum is here, is minus 3/2. So this flux is sitting here, pi, this is the energy flux, and mean magnetic field B naught, and the exponent is minus 3/2. Okay, so 5/3 and 3/2 are different, and I remember Professor Verma from PRL, director, he said, why are you worried about 3/2 and 5/3? The numbers just, but the problem is that this is the different phenomenologies. So it is like a full theory behind it. We call it 3/2 or 5/3, but there's full formalism connected to 3/2 and 5/3. Okay, now let's try to do the field theory. So I just try to sketch it. Okay, I mean just to give a flavor of it. So if you look at the equation for the velocity field u dot, okay, so ui, so I is a component, na 1, 2, 3 standard. So the right hand side, the nonlinear term, I just take the nonlinear term del j d. So this u dot grad u, and we also the term b dot grad b del j bj bi. Okay, and pressure gradient and so on, but we can't put all of them, so they will be too confusing. So I just put that. So now we write the Feynman diagram for this. Okay, so it is, what is Feynman diagram? Is basically this one for velocity uj and one for ui. So this is a notation. Okay, we just write like that, and for magnetic field we write dashed lines. Okay, like this. Now of course, so this is ui dot, but I will say that, well, if I do I assume the velocity field to be random, and if I do average, then I'll get 0 to this order. This is, well, you'll get 0. I say, well, I go to the next order, I do some perturbation. So what is u? Now again uj I will write, uj dot. So uj dot will again involve ur, us, del r, right? So now this one velocity field is a Green's function, so we write this as a Green's function times 2 u's. Okay, now this is a field theory. Okay, so we write one of the u's is replaced by Green's function and 2 u's, and 1 u coming from here. So these are 3 u's, 1 u has become and 2 u's here. So this is a correlation function u, okay, and this is Green's function, and this is 1 u here. Okay, so this is what we get. Okay, now same thing for here, Green's function coming from 1b, this is a different Green's function than this. Okay, and we get 1 here, and now like that. Okay, now this is, now I need to put viscosity here, minus nu k squared in Fourier space, and d by dt minus I omega. Okay, so now what this term does, so this is called self energy term. Okay, this is the one term, is proportional to u, and left hand also is proportional to u. You see, this is u, and nu k squared. So what this term is doing is telling you the correction in viscosity. So you see, this linear term has ui term here, but let's say this is a number, this is basically a number, and then we have a term which is proportional to u. So you can take this to the left hand side and you say, well, u nu plus delta nu. So these are renormalization of viscosity. Viscosity is enhanced by turbulence. In fact, this is indeed true. The diffusion, if there was no turbulence, will be very weak, but because of turbulence, the diffusion is enhanced. Okay, so this is how we follow the procedure, and we get viscosity. And it turns out both nu and eta, this viscosity and this thing, these are scaling. We assume some ansatz, and this is k minus 4/3, epsilon 1/3, and this is a constant nu star. Okay, and this eta star. So the idea is to compute them. This is very, I mean, it took me several years to compute them, and we compute the stuff, nu star and eta star, and these are useful quantities for large eddy simulations. We use it in real simulations. Okay, we use these quantities to simulate for larger Reynolds numbers. Okay, now we can also compute Kolmogorov constant for MHD. This was done by another calculation, so which I will not. So it's again pretty involved calculations, but this is how we close what Chandrasekhar was wanting to do. So it's self-consistent. Some of you, I mean, I'm not sure there is any field theorist of condensed matter physics like Professor Rajaraman would be doing this stuff. So we have Green's function. Remember, I wrote Green's function, and there was a correlation function. So to close it, we assume this to be full dressed Green's function or renormalized Green's function, and this to be that, and we assume that it is phi third. So it is called self-consistent field theory. And it's possible to close it. Okay, of course there are assumptions for the relaxation times, as well as for this is another assumption that we assume that all these large number of diagrams are compressed into a single diagram. Okay, so if you do that, then it's closed. So the field theory of MHD is to first order. It could be done. And it has some interesting results. Unfortunately, this paper took me, there were 5 rejections of journals, so it was finally published in, the whole detailed paper is in Pramana, but one in PRE, and physics reports finally got some attention, but there's no taker. Okay, I mean, nobody wants to do field theory because it's of course very involved. Now just a few words, why Kolmogorov theory for MHD? Because Kreknin said that mean magnetic field is important, B naught. And as a result, the time scale is 1 by k v naught, and the spectrum is k minus 3/2. That is the spectrum Ek. And the prefactors are important, k v naught to the power half. Now, so in fact, by the way, people believed this Kreknin theory till 94 when I was a PhD student. In fact, Kreknin is Kolmogorov and Kreknin. I mean, in turbulence theory, these are the 2 big names. I mean, so to confront Kreknin is I mean, Kreknin said something. This is 1965. Okay, and the year I did not put. This 1965. He showed this theory, and no questions asked. That was done. But there were observations from solar wind, which was clearly saying that it's phi third or not 3/2. Okay, but there were some massaging and so on. But anyway, so why does phi third work? What is wrong with this theory? Okay, so Kreknin theory, something is wrong. So this is my 99 paper. So this mean magnetic field. Now what Kreknin assumes that there is an alphane wave which is affected by the mean magnetic field B naught. This stuff. Okay, so that is 1 by k v naught. But if you look at it slightly more carefully, then we have waves within waves. So there is one alphane wave, but within that there is small alphane wave. Of course, within that there is tiny alphane wave and so on. There are tiny alphane waves. So now just look at this wave. Is it affected by this red mean magnetic field or affected by all other magnetic fields? So to tell you the stuff, in IIT we are affected by local administration more than Prime Minister. I mean, of course, we get our salary from the central government, but there are local effects as well, and local mean magnetic field, local director and deans, their decisions matter more, right? So similarly,
Try to conclude soon.
yeah, I will. So this mean magnetic field, so here B is basically affecting the alpha n wave is renormalized. So in fact, local magnetic field is what appears, and so here B naught is K dependent, and we should substitute this B naught, then we get phi third. Okay, so that's what we get. So that's stuff. So just to say a few words, this is Chandrasekhar's book. Okay, the very famous book. In fact, it's really the so the story is, I was in Paris with French collaborators, and was said, well, where is this result? They were quoting a result. Then I said, where is the result? Then he said, it's in the Bible. So I was a bit shocked. I mean, how is this hydromagnetic field in Bible? I said, what do you mean? They said, you don't know Bible? It's Chandrasekhar's book. So that is what is respect of this book among the community. Okay, so some of the derivations I have done it here, but I could say that the derivation in my book is much simple, is much shorter, and because I use something called Kriya Herring basis, which is again technical thing, but I'm just advertising some of the stuff. So like rotating turbulence derivation is just 1 page, but if you look at the original derivation, it's like 10 pages. Okay, it's huge. So with after that I just conclude. So MHD turbulence is better understood now than before, but these are the people who who pose the problem, and then he said, well, how to solve this problem. So and he, like, this book on hydrodynamic harmonic stability is really the benchmark book, and I believe on this, but there are of course competing theories like -3/2 still proposed by a lot of people, and strong B naught, this is still remains a problem. If you have a very strong magnetic field, then it will be anisotropic, and there could be weak turbulence effects. So this remains a challenge. Okay, so with that I will close it, and again thank the organizers for wonderful meeting, so that I could meet people here and for present this. Okay, thank you for your attention. Okay, I conclude, and I welcome any questions or comments. Professor Lakina, it's
The talk is open. The talk is open for questions. You can raise your hand, or you can ask directly question to Professor Verma. So I have one question, Professor Verma.
Yes, please.
If suppose there is a finite viscosity in the medium,
Okay.
so in that case, how the MHD turbulence get different than the non-viscous case?
No. By the way, for all my work or all Chandrasekhar's work, everybody, turbulence, we need viscosity as well as diffusivity to generate the cascade. So all this work, when I wrote that, I didn't. I mean, there's viscosity plays a key role. So cascade is possible only when there's viscosity. So there must be somebody sucking the energy. There is no sucking the energy, then there is a different theory, and that is not normal turbulence. Okay. So everywhere there is a viscosity. Okay.
Professor Vinod?
Yeah, Mahinder, thank you
Okay.
for a very nice talk.
Thank you.
Especially listening to you after a very, very long time. This debate between k to the -3/2 and -5/3 is an ongoing debate, as you said.
Yes.
And I think one of the solutions, it was kind of accommodating both by saying that one is relevant in weak turbulence case, in which B0, as you mentioned, would be important.
Mhm.
And but in the strong turbulence case, it would be more like Kolmogorov dimensional analysis,
Mhm.
and the both can coexist in different ranges of the strength of the turbulence.
Right. So shall I comment on that? You're done with
Yeah,
the question?
please.
Yeah.
Please.
So
Please, I would like to hear you.
yeah. So for strong B naught, it is not minus 3/2. So there is a work by Nazarenko, Galtier, and so on. It is K minus 2. K
Not,
per
sorry.
Galtier.
Sorry.
Galtier, they did this in 2000, and they found that weak turbulence theory gives you K minus 2, K per minus 2. Is not 3/2.
Sorry, Mahendra, can I interrupt?
Yeah, please.
Can I interrupt?
Yeah.
Yeah. So I didn't mean strong B0. I meant because in strong B0, of course, the two-dimensionality comes and so on, as you have already mentioned, and
Right.
isotropic comes. I was mentioning strong turbulence. See, like for example, if the amplitude of the fluctuation is comparable to the ambient field.
Right.
So strong. I was mentioning strong turbulence. Not
Yeah.
strong
No, I
B0.
understand. So in fact, there are several theories which I didn't say that there's Bill Matthews and Zoe, but so B naught dot red U and so on. If you just keep this term, then the theory basically boils down in modern days, okay, to minus 2, okay, and of course the other terms are weak. So this is what is done in this paper. If you say that this is not so strong, and then we keep the nonlinear term, then it is 5/3. Now, of course, there is a paper by Balderev in Chicago, Wisconsin medicine. He is bringing back 3/2 by not by weak or strong argument. He is bringing by some cross correlations. U dot B plays a big role, and that is a theory, which is, I don't quite believe that, but anyway, that is what is it. But so I think Professor Vinod, that is almost gone. That Cregnan is wrong, I believe. But Balderev is trying to reconstruct a different form of 3/2. It is not Cregnan argument, but Cregnan is wrong. It's known now from my RG argument as well as by this weak turbulence argument. So I think there a lot of water has flown through the river, and those old theories are not applicable anymore. That's my personal take, and I think a lot of people will agree with me. But whether Balderev is wrong or not, we need to prove it. Like for us, RG theory we could not really do numerically, but we are trying to do it now. So verification of that.
Good.
Yeah.
Thank you.
Thank you.
I have a small question.
Yeah,
In
please.
solar wind,
Yes.
they say that inertial spectrum is Kolmogorov type.
Yes.
But when you go to a shorter wavelength,
Yes.
then kinetic Alpine waves become important.
Yes.
First there is a break, and then final dissipation is by kinetic Alpine.
That's right.
Is it true or?
Yeah, I mean there is strong evidence, and a lot of people believe that. I think there is a minus 5/3, then minus 3, then exponential. So minus 3 is there. This is kinetic Alpine wave. So there is a dissipation mechanism. I mean, of course, yeah. So there is dissipation, and minus 3 is. It is minus 3 or not, that is a debatable, but there is a.
Yeah, that is debatable, but there is a break in
Yes.
spectrum.
Yes, indeed.
Okay, any more question?
Yeah. Can I?
Yeah, I have a short question, please. We'll go for the next talk.
Okay. Yeah. Go ahead. We will discuss later.
No, I have a short question, no problem.
No, I just wanted to remind Mahendra that if we, for example, include Hall effect in the idea in the MHD equations, then of course the time scales differ because of the nonlinearity of the Hall effect, and then we and also in the solar wind this 11/3 index is also observed. So as you said, it may be between 3 and 4. Lakina also mentioned 3 and 4. So that could be explained by not really going to kinetic Alpine waves, but including the Hall effect itself.
Indeed. I think Hall MHD is getting some attention now in turbulence community. So good. So I think you worked quite a bit on Hall MHD, and we should get into that and what is the evidence of that, and try to push your exponent.
I need your help.
Yeah, I will. I am always here. Yes. Okay.
Now I think there will be one last question from Professor Rampal Sharma. Professor Sharma, please go ahead and ask question.
Yeah, thank you very much. People are talking in solar wind, say, for example, Professor Verma,
Yes.
that current seeds are also responsible for this steeper power spectra.
Okay, so dissipation. So okay, now let me make one important remark.
I mean reconnection and recurrencies.
Yeah. So Kolmogorov theory is considered to be universal theory. Okay. Why is it universal? Because inertia range is independent of dissipation mechanism. Okay. So that 5/3 is independent of whatever dissipation takes place. That's the beauty of the theory. Now dissipation could be Hall, like Vinod is telling. There could be kinetic alpha wave, or it could be cyclotron damping or Landau damping. All of it could be there, and they will have their own effect. But 5/3 is independent of it. So that's what universal is about. So indeed, I mean, current sheet can have their own effect, no problem. But universal theory is not talking about it. That's what please keep in mind. Not Chandrasekhar was trying to get to the inertia range part.
Okay.